Hello. All right. I know everyone's super tired. Hope you got your coffee. I earlier asked the audience to come up and present. That's how tired I am. So I think we're going to get started. Same routine as before. Let's take it away.
Hi, everybody. My name is Masha Itkina, and the problem that I'd like to talk about today is that neural networks can often be overly confident in their predictions, especially when faced with out-of-distribution inputs. This can be problematic for safety-critical systems, for example, autonomous vehicles. To identify out-of-distribution inputs, what we want is the neural network to estimate the epistemic uncertainty or the model uncertainty, in this way achieving a level of system self-awareness. What we do in this paper is we estimate this epistemic uncertainty using a method called evidential deep learning. And we do this in one shot for the task of trajectory prediction. What we also do is we introduce an interpretable paradigm into this estimated epistemic uncertainty, where we distribute the uncertainty amongst the semantic concepts, past agent behavior, the road structure, and the social context in the scene. What you see in the figure shown here is an example where we have out-of-distribution trajectories be faster and in-distribution ones be slower. Our algorithm successfully estimates the epistemic uncertainty to be higher for the faster out-of-distribution example, as shown by the lower alpha-0 values in the figure. Our code is online. If you'd like to learn more, please come by my poster, paper number 54. Thank you.
Hi, everyone. The ability to perform diverse grasps on arbitrary object is a key manipulation skill. A multi-finger robotic hand is superior to simple grippers in its ability to achieve a wide variety of grasps. However, planning multi-finger grasps is challenging due to the multimodal solution space stemming from rich physical constraints. In this project, we combine learning and optimization to compute grasps for diverse objects with a multi-finger hand. First, we use a conditional variational autoencoder to predict finger placement given object point clouds. Next, we formulate a novel bilevel optimization problem to solve for grasp configurations satisfying kinematic and dynamic constraints. Our CVAE was trained entirely on synthetic data, but our method deploys directly to the real world, achieving over 85% grasp success rate on 20 seen, unseen objects with novel geometries. To learn more, please stop by my poster. Thank you.
Hello, my name is Alexander Gorban, and I'm happy to present our work on semi-supervised 3D human key point detection with the autonomous vehicle. For some reason, there are too many robots here, too few people defending the interest of humans. So I'm hoping to represent humans and make sure that autonomous driving system performs safely around humans. So we present. It's a very quite fast developing area to detect 3D key points using camera images, but there are not so many methods detecting 3D key points using LiDAR images and camera images in the wild. So in this work, we present a fast, robust, and compact method to detect 3D key points, which could be used to improve behavior prediction and human understanding for self-driving cars to make them safe for humans. Please come to our poster.
Hi, everyone. Dense visual descriptors have been shown in the past to be a highly flexible representation for objects, which can work in a variety of downstream tasks. It can work with deformable and articulated objects as well. However, prior work often relies on the presence of complex data sets, such as RGBD sequences, CAD models, annotated data sets. In our work, we want to, however, try to see how far we can get by just doing contrastive learning on a set of unordered and unlabeled RGB images, for example, obtained from a robot cell, which you might encounter in an industrial setting. If you come to our poster, you will see when and how this approach works, what the limitations are, when it might fail, and the advantages. For example, you can train this on objects where depth data might not be present, such as reflective objects or thin ones. And you will also see when this might actually not apply to your use case. Thank you very much.
Hello, my name is Denis Hadjivilishkov, and this is Of Course. Of Course is our model for one-shot semantic part segmentation from a single example without any fine-tuning. In this work, we provide a single example of an object, for example, a knife, and an annotated area of that object that we are interested in. For example, the blade or the handle of that knife. And we find the correspondence of those parts in a novel example that could be from the same class or from a different class, as long as it has a similar part. And we use this in a robotic setting that is shown there in the corner of a pick and place task with predefined skills to show that we can use the corresponding, semantically corresponding parts. And we're currently working on extending that with imitation learning. If you're interested in learning more about this work, come to poster 42. Thank you.
Okay, do you want to order your robot to get you lunch by simply saying the words and not defining a reward function that has 10 different terms? Do you want to not annotate thousands of trajectories with several R's of human annotated labels? Well, do I have the paper for you at paper 21? We're presenting LMNav, or large model navigation, which uses large pre-trained models for instruction following in the real world. Our system has 3 models. The first is a large language model that can parse and translate text, but has no context of embodiment or images. The second is a visual navigation model that can ground images and text, but has, again, no context of embodiment. And the last is a visual navigation model that can control the robot from visual observations, but doesn't really understand text. And putting it all together with a few neat tricks, we get an instruction following system that does exactly as you say in the real world. Yeah, I won't spill all the beans, but please come to my poster. It's right under us in the poster session in the lobby downstairs. Thank you.
Hi, my name is Hao. I'm a master's student from Stanford University. I'm going to present our work, See, Hear, and Feel Smart Sensor Fusion for Robotic Manipulation. So we introduced a multi-sensor robot system that sees with a camera, hears with a contact microphone, and feels with a gyroscope sensor. We also proposed a self-attention mechanism to fuse all 3 modalities to solve two robotic manipulation tasks, dense packing and pouring. So we also analyze the aggregate attention scores and demonstrate the characteristic of each sense. So here's an example of the dense packing task. You can, the goal is to insert an object into the box. You can see that different sense dominate at different stages. And here's an example for the pouring task. The goal is to pour beads from one cup into another. Audio plays an important role in this task. Thank you. Please, if you're interested, please come to poster 250.
Hello, my name is Jackie. My poster is all about contact-rich manipulation. So how do we get robots to reliably manipulate objects in constrained environments? So think shelves and cabinets. It's very common in human environments, but in these cases, the robot cannot always just directly grasp the object. And so we need to use diverse non-prehensile behaviors. So think sliding, pushing, pivoting, and toppling. It turns out that hybrid force velocity controllers are a very expressive tool that can allow us to express all of these diverse non-prehensile motions. However, when we try to use HIVCs in the real world, they don't always succeed due to a lot of the approximations that we have to make. So that's why what motivates us to learn this precondition function that tells us when an HIVC controller will be successful and when they will not be successful. With the learn precondition function, we can filter out the actions and help us do multi-step planning. So if you're interested in contact-rich manipulation or just about the intersection of learning, planning, and control, come find us at the posters. Thank you.
Hi, I'm here to talk about our work on human-robot commensality. 27% of people in the US have a disability, and many need help with activities of daily living, such as feeding. When talking to people with mobility limitations, we were almost unanimously told that eating with friends and family are some of their most memorable eating experiences. But for social situations, current robot-assisted feeding systems would require a manual trigger and are socially disruptive. Commensality is the act of eating with others and is a delicate dance of multimodal signaling. In this work, we focus on when an assisted feeding robot should feed a user in a social dining scenario. We call this human-robot commensality. And to do this, we created this data set, which contains videos of people eating together. It has 18 hours of video in 30 triadic sessions. And then we train a model to predict when a user intends to take a bite of food. And then we modify this model to use on a robot that learns the social group dynamics from other co-diners. We then deploy it on a robot for a user study and find that people prefer our model to other baselines. Please check out our poster. Thank you.
Hi, my name is Joanne, and I'll be presenting our work, Rethinking Sim-to-Real, Lower Fidelity Simulation Leads to Higher Sim-to-Real Transfer and Navigation. In our work, we ask the question, can Sim-to-Real transfer be improved by decreasing simulation fidelity? So to do so, we train navigation policies with two physics fidelities, kinematic, which uses Euler integration, and dynamic, which uses simulated contact dynamics. We deploy both policies to the real world on a spot robot, and we find that the policies trained with a lower fidelity or kinematic physics achieves a success rate of 100%, whereas the policies trained with the higher fidelity or dynamic physics achieves a lower success rate. And in investigating why the kinematic policies outperform the dynamic ones, it turns out to be due to scale. So although the kinematic policies are trained for much less wall clock time than the dynamic policies, it's able to learn from much more experience, which is ultimately better for RL policies, thus leading to higher sim-to-real transfer. For more questions or comments, please come by my poster. Thank you.
Hello, everyone. My name is Kamil, and today I'm going to talk about LiDAR, laser sensor often employed in autonomous cars. LiDAR uses horizontal lines to scan the scene for depth information, and LiDARs with large number of lines are expensive. We suggest a new problem. Can we build a LiDAR with fewer lines and reconstruct depth information on par with a LiDAR that has larger number of lines? In our paper, we say, yes, we can. We know that certain parts of the scene contain higher frequency structures than others, requiring more lines, and vice versa. We propose a game theoretical approach based on the Shapley value. We also incorporate space constraint, which proves to be essential for the depth completion task. If you're curious which lines are the most important, please come to our poster in the poster lobby, number 43. Thank you.
Hi, everyone. My name is Carl Parrish, and I'm excited to present our work on cross-domain transfer via semantic skill imitation. The goal of this project is pretty easy. What we want to achieve is that we want to take demonstrations from one domain and use them in a different domain. And this should be across environments and even across agents. So that in the very end, I can basically take this video at the bottom left, which I recorded with a GoPro on my head in my own kitchen, and use it to teach a robot in a different kitchen how to do the task I wanted to do. The way we do this is that we take in the wild human videos to learn about human skills, and then we take about robot skills. And then we can take the demonstrations, extract a prior over the skills, and then use it to guide policy learning in the target environment. We're pretty excited about this because it will allow us to reuse demonstrations and to also collect them much easier if we can do it with a human. There's a few details on how to make this work. So if you're excited about training a robot with videos recorded in your own kitchen, please come see me at my poster. Thank you.
Hey, my name is Katrin, and in the following poster presentation, I present Plant. Plant is this guy over there. So in self-driving, simplified driving stack could look like this. So we have a perception module for object detection and tracking, and we have a planning module for path planning and collision avoidance. And in previous work, in the planning module, it was often done in like a handcrafted rule-based system, which does not really scale. Or it was done with a bird's eye view image together with a ConvNet, which is computationally very expensive. So in our work, we investigate how we can do a low dimensional representation and train a transformer. So Plant can not only thrive in an urban environment, but can also show on which vehicle the decision is based on. So for example, here, the white or yellow boxes has a low relevance and the red boxes have a high relevance for the driving decision. So if you're interested in how we're doing this, come and check out our poster. Thanks.
Hi, I'm happy to introduce our work, manipulation via membranes, high resolution and highly deformable tactile sensing and control. Our method learns of tactile sensor membrane deformation dynamics in order to control a grasp, tool pose, and forces transmitted to the environment during contact-rich manipulation tasks, such as drawing with a grasp marker or in-hand pivoting. Tactile sensors like the soft bubbles provide high-resolution contact feedback. Moreover, they are compliant, allowing gradual force transmissions. However, they introduce complex dynamics between the grasp object and the robot, like relative motion and potential slip. Our method accounts for this by modeling and controlling how these membranes deform as a consequence of robot actions. If you would like to know more details, please stop by our poster at room 041. Thank you.
Hi, everyone. This is Perceiver Actor. So in case you haven't noticed, transformers are taking over everything. It started with NLP, where language models were encoding 1D tokens. Now vision transformers encode 2D image patches. But what's the right problem formulation for robotics? Since robotics is obviously more than a 2D problem, maybe we should encode 3D voxel patches. That's exactly what we do in Perceiver Actor. We train a transformer to detect 3D actions by encoding voxel patches. And we can learn a single transformer policy for 249 task variations in RL Bench. This includes everything from screwing light bulbs, pressing buttons, stacking, sliding, sweeping, placing, turning. Does it work in the real world? Don't you really need a lot of data to train transformers? You can actually train one from scratch with just 53 demonstrations. And you don't have to take my word for it. The paper, code, model, everything is publicly available. You can try it out yourself. Thank you.
All right. Hi, everybody. I'm Sunil, and today I want to talk about how we can learn multitask policies by learning latent object affordances from human play data. So play data consists of unstructured and undirected demonstrations across multiple tasks. It's cheap to collect, and it provides broad state action goal coverage. In Plato, we view play as a sequence of object interactions consisting of a pre-interaction phase, an interaction or object affordance phase, and then a post-interaction phase. We can sample varying and long horizon goals from the post-interaction, and then we can encode the interaction into a latent affordance Z. Then we can learn a policy that operates over varying horizons that conditions on the future affordance and goal. So we evaluate Plato in a set of challenging 3D manipulation tasks involving diverse objects like mugs, blocks, cabinets, and drawers. And Plato substantially outperforms the learning from play baselines. So come check out our poster for more details. Thanks.
Yes, hi everyone. I'm Young-Do and I'm here to present our work, Masked World Models for Visual Control. So Dreamer learns world models via image reconstruction, but it can often fail on tasks with small objects. So why is this the case? So this is because Dreamer learns a single model that does both image reconstruction and future prediction, but each task itself is already very difficult. So our idea is to revisit the idea of decoupling visual representation and dynamics learning. So we first learn a masked autoencoder on top of convolutional features, along with reward prediction to encode task-relevant information. And we also learn a world model that reconstructs autoencoder representations instead of raw pixels. So we report the results on MetaWorld, RLBench, and Domain Control Suite. So visit our poster session for more discussion. Thank you.
Hello, everyone. I'm Yuzhou from UC San Diego. Today, I will introduce our work, DexPoint, generalizable point cloud reinforcement learning for sim-to-real dexterous manipulation. So in our work, we will consider two types of manipulation tasks, grasping and door opening. The robot arm and the multi-finger hand need to coordinate together to solve this manipulation task. In this video, the blue and red points on the left side of each manipulation video are the point cloud observation. So in our work, we introduce reinforcement learning algorithm, which takes the point cloud as input for manipulation task. Our point cloud-based policy trained purely in simulation can successfully generalize novel objects and transfer to real world. So in the real world setup, we attach a legal hand on XM6 with a real sense camera, and our policy takes point cloud, robot pre-perception, and goalpost to predict the action. So feel free to drop by our poster at room 040. Thank you.
That's it for the spotlights, but we have a quick announcement from Oliver.
Very much. I just want to remind everyone that we're going to have one last session in here. We're actually going to push it back to 5:30 just to give a little bit more time for the posters. And it's going to be the open problem session. So I hope to see lots of you there and ready to discuss some problems.